All right, guys. So we're going to go over implicit differentiation. So I'm going to kind of explain what it means and why we're doing it, and then we're just going to practice a couple of problems. It's not necessarily a hard concept. It's just a relatively tedious. In other words, you have to really keep track of what's going on when we're dealing with implicit differentiation. So the idea is this. So let's say we're given this type of function. Well, this type of equation, it's really not a function because if you drew it out normally, it would have this loop like this. And then technically it's not a function, so we couldn't take the derivative of it. But we have this way to take the derivative of it, and what happens is that there's like 3 hidden functions inside of this equation. So if you can imagine, this dotted line is a function, and then this curved brown line here is a function, and this bottom orange line is a function. So I could find the slope at these 3 points, here, 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 right? So I could find the slope of this one, I could find the slope of that one. Should probably do it in some sort of different color. I could find the slopes here. But the problem is that these are hidden, so I don't have a direct path to the derivative. Like, let's say if this was an x squared one, we could just take the derivative of x squared. Kind of see how it's kind of shaped like a parabola. We could take the derivative of x squared and then find the slope at this point. This one here has got a slight curve to it. Let's say it was a negative square root function. We could take the derivative of that negative square root function and find this piece. So, because those are explicit, they're very straightforward. So we've been dealing with explicit equations. Now what happens is we are going to do what's called implicit differentiation. So basically, implicit means that it's kind of hidden. So we're going to differentiate equations that have hidden functions inside them to where we can find multiple points of their slope. That's why it's called implicit differentiation. It's kind of like we're finding the hidden ones inside there. So let me grab my towel here real quick, and I'm just going to do a couple of examples with you guys. So here's the biggest thing. Take the derivative. That should say derivative. Derivation's fine, but derivative. Okay, and whoa, what was I thinking? Play dy dx for every, I don't know what I was thinking. Dy dx for every derivative of y, I don't know what I was saying there, guys. Move dy dx to one side and solve dy dx. All right, so let's take our first example here. Let's just take something like y squared equals x. So we can leave it just like that. So off to the side here, if I just said y equals 3x squared, right? This is y to the first, so y is 1. 1 minus 1 is 0. The derivative of y is dy dx, and then that becomes 6x. This is y right here. We get dy dx, because every time I take the derivative of y, I find dy dx. So I find dy dx. So we're still working with the same thing. So let's just work with some terminology. We'll add some terminology. So I want to take the derivative. This means take the derivative of the left side, and I want to take the derivative of the right side. So let's just apply the power rule right here. So I get 2y, and then I need to make sure when I take the derivative of y squared, I get dy dx. Okay? then now I'm going to take the derivative of x, which is just 1. So I'm left with this dy dx. Well, I solve for dy dx. Luckily, this is all on one side, so I solve for dy dx, and I get dy dx equals 1 divided by 2y, and that's my... So I can find the slope anywhere on this as long as I have the value of y, okay? So that's implicit differentiation. We're not worried about extra y's inside the problem. So let's tackle another one here. And that becomes like when we're dealing with a circle. Let's do a circle here. X squared plus y squared equals 25. X squared plus y squared equals 25. Okay? So this is a circle with a radius of 5. So technically, if we look at it, we've got a circle here, and then we've got a circle here. So we have a function on top that's usable, and we have a function on the bottom that's usable. The reason that it's only half, that's why your calculator can only graph half of this. And if you put it in your calculator, it won't work because it will only graph functions. But remember, there's 2 hidden functions in there. There's a top and a bottom. Well, when we deal with it implicitly, we're able to solve it. So let's just work with what we got here. So we're going to take dx of both sides. So we're going to do x squared plus y squared. And that's going to equal the derivative of 25. So now I'm going to take the derivative of x squared, which is going to be 2x. I'm going to take the derivative of y squared, which is going to be 2y, I applied the power rule, dy dx equals 0. The derivative of 25 is 0. So now I got to solve for my dy dx. So let's move some things around. 2y dy dx equals negative 2x. Now I solve this. Dy dx equals negative 2x over 2y, and therefore my derivative is x over y. Which makes sense. I got to have both points on this. So it's, negative. This is my negative x over y. So I will find my slope. This equation, or this derivative, will find my slope anywhere in the hidden functions. That's the idea behind implicit differentiation. So let's try one more, just to see what we got here. Okay? All right, so all right, 2y equals x squared plus sine y. 2y equals x squared plus sine y. All right, so let's tackle this here. So this is ugly. We know it's ugly. Look at it. I mean, it's just flat out ugly. So let's just take our equation here, and we're going to go take the derivative of both sides, and we're going to do 2y equals the derivative of this right side, and that's going to be x squared plus sine y. All right. So if we take the derivative of this, my 2 is going to stay, because 1 times 2, 2, and then, oops, not that color. We have 2, and then the derivative of y is dy dx, that's our key piece right there, equals the derivative of x squared, which is going to be 2x, plus the derivative of sine, which is cosine y, times its derivative of y, which is dy dx. So now we've got to do a little bit of extra work. So dy dx, sorry guys. So now I got to move this to the left side. So I get 2 dy dx minus dy dx times the cosine of y equals 2x. Okay, now I can factor this out, and we get dy dx times 2 minus cosine of y equals 2x. So dy dx is equal to 2x over 2 minus cosine of y. Okay? So, that, my friends, is in a nutshell how to deal with implicit differentiation. Remember, implicit differentiation is just finding a way that creates a relationship between x and y to find hidden functions or hidden derivatives for functions inside crazy looking graphs. So if you notice, when we solve for the derivative, we need x and y on almost all of these. So make sure, follow the steps. Take the derivative, both sides, that's what this is, it means take the derivative. Find dy dx, not sure what I put here to begin with, dy dx for every derivative of y. Take the derivative of y, make sure you put dy dx. Move all the dy dx's to one side. You're going to factor dy dx out, solve for dy dx algebraically, and then that's our plan for implicit differentiation. Good luck, guys.